Well, howdy folks, here we are, another lab from the barn. Today's lab is kind of an extension of the one we did last week on Lewis structures, where I built the molecular models for you and you had to predict shapes of the molecules. Today what we're going to look at is a little deeper into that sharing of electrons between nonmetals. I mentioned that when they kick their electrons into a common space and share them between the two atoms, that they now count for both atoms in the rule of 8. But we didn't talk about physically how those orbitals actually combine in order to form a bonding orbital between the two atoms. So let's begin our discussion today right there. All right, so when we begin to look at how orbitals actually overlap physically to create a common space where two atoms could share a pair of electrons between them, we find that there's two spatial orientation ways that the orbitals can actually overlap. One of them is kind of a head-to-head overlap where the lobes of the orbitals go directly at each other. And the other is kind of a side-to-side overlap of orbitals. Well, this first type, this head-to-head overlap, is referred to as sigma-type bonding. All right, so essentially, if two p orbitals were to come together and form a common space between the two and overlap, that would be a sigma-type bond, a head-to-head overlap of orbitals. Let me draw a quick picture and show you what I mean. Okay, well, two very common ways for a sigma bond to form is for two p orbitals to come and point directly at each other, where the two lobes essentially can sort of occupy the same space. And so when they approach one another, each with an electron in it, what happens is the middle of this kind of swells up and creates a common space between the two nuclei. Remember, these p orbitals are dumbbell shaped with the nucleus right there in the center. So consequently, the bonding, the sigma bond orbital that's created between the two atoms essentially looks like this. Now, what typifies a sigma bond is the fact that there's now a high traffic area of electrons right along what's called the internuclear axis, the line that connects the two nuclei. All right, so this does create kind of a high traffic area right between the two nuclei, and that's typical of a sigma type bond where you have this head-to-head overlap of orbitals creating that common space. But this can also happen with a p orbital and an s orbital. Now, when a p orbital approaches an s orbital and they're going to share a pair of electrons, each one bringing one to the dance so that they can kind of kick those into the common pool and share them between themselves, like a hydrogen atom. Hydrogen atoms usually just bond with their s orbital. They just have that one valence electron. Sure enough, this is how they form a sigma bond. All right, well, essentially then the orbital of the p, that lobe of the p orbital envelops the s orbital. And consequently, when they share electrons, now this common space sort of looks like this, sort of ballooned out over that s orbital, sort of swallowing it up. And that pair of electrons now can literally orbit both of the nuclei, fooling both of the atoms into thinking that they own that shared pair of electrons. All right, so all we've done is just taken this another step and kind of showed, well, this is the type of overlap that happens when these shared pairs of electrons happen. Now, what makes this lab a little different is we're going to begin to look at what are called hybrid orbitals. They're no longer going to look like p orbitals or like s orbitals. They're going to end up looking like something sort of in between. So let me draw a quick picture of that. Okay, well, this lab introduces a special kind of overlap. These are hybrid orbitals, and they're a cross between the s orbital and the p orbital. Remember, s orbitals are spherical shaped. The p orbitals are those full dumbbell-shaped orbitals, but the hybrids are kind of in between. They've got a small lobe and a large lobe. Now, this happens in a lot of bonding, and it explains a lot about the shapes of the molecules that we discussed last week. So this is going to kind of help us fill in a few of the gaps that we left with last week's lab. Now, it turns out that these hybrid orbitals, sure enough, can sigma bond with another p orbital, or they could have a head-to-head overlap, create a big ballooned space in between where that shared pair of electrons could exist. But in addition, it could also sigma bond with an s orbital. And again, that large lobe could essentially envelop the s orbital and create a common space where electrons could be shared. Okay, so a direct overlap of orbitals leads us then to a sigma bond. But I mentioned that there were two ways that this happened. So let's look at the second mechanism by which orbitals can actually overlap with one another to create that common space. Okay, the other type of orbital overlap that we need to discuss is pi bonding. Now it turns out that p orbitals, and this only happens with the p orbitals. It doesn't happen with s's. It doesn't happen with the hybrids. You need this full dumbbell shape for this to occur. It turns out if two molecules have p orbitals on them and they come close to one another, two atoms, then essentially the orbitals can overlap side to side. And you see that suddenly you've got this common space that's created above and below the internuclear axis. So unlike the sigma bonds where the electrons now were in high traffic area right between the two nuclei, here it creates a high traffic area above and below the internuclear axis. That shared pair of electrons can still orbit both the nuclei, both thinking that they own that shared pair. But this is definitely different than that head-to-head overlap of orbitals in order to make a sigma bond. And the big difference here is that hybrid orbitals form sigma bonds because they have one big lobe that sticks out into space and things can latch onto the end of it. They cannot form pi bonds because they need this full double dumbbell shape in order to do that. So it turns out that only leftover p orbitals that we find in the molecules form these pi-type bonds. Now I want to show you just a quick example of this, but of how sigma bonding and pi bonding can occur. But I'm just gonna bend the truth just a little bit, and I'll show you where. Okay, well, suppose I were to bring, let's say, two carbon atoms together. Now, carbon atoms have p orbitals, one along the z-axis, one along the x-axis, and then one in and out of the board. I'm just going to draw it as a line, because if I draw another lobe, it looks ugly. But in and out of the board, there'd be another p orbital that's there. If the other carbon atom had likewise, one along the z, one along the x, and then one along the y. As I bring these two sets of p orbitals together, can you see that there's only one set that's oriented in such a way as to form a sigma bond? Those would be the ones along the x-axis because there's a potential sigma bond overlap here head to head. All right, so it turns out that, yeah, whenever a single bond forms between two atoms, the first and easiest one to form is a sigma-type bond. So it turns out if you have a carbon that's single bonded to another carbon, that first bond that forms there is of the sigma type. However, suppose that there are electrons left over in the z orbital, the one that's along the z-axis. Well, now that we've established these two are pointed directly at each other, the z's would have to overlap side to side if I brought these closer together. And so there would be a potential pi bond that could form that's in the plane of the blackboard. All right, so that simply means that if there's a secondary bond, a double bond, that second one is generally of the pi type. The first one to form is always of the sigma type. So that means whenever we had a double bond, it was taken care of by unhybridized p orbitals because they still have to have that full dumbbell shaped. Remember, we could use hybrids to form the sigma, but we can't use hybrids for these pi bonds. That becomes kind of important to our game here in a minute. All right, so you can understand then that a double bond would be a sigma and a pi. Well, what about a triple bond? How could that happen? Well, can you see then that there's still the py orbital that's in and out of the board that are parallel to one another? They could conceivably overlap side to side and form a pi bond that's sort of in the plane in and out of the board, creating almost like a tube of pi bonding electrons with a sigma bond going right down the center of that. All right, so it turns out, sure enough, if you have a triple bond between two atoms, only one of them is sigma, the other two are pi. And again, only because of the orientation of the leftover p orbitals, you essentially could only have one set that would point directly at each other to give you a sigma bond. All right, so this is kind of a general rule of thumb then. When you're drawing Lewis structures, first bond between two atoms, always of the sigma type. All right, well, in that last example where I had two carbon atoms come together and showed how their p orbitals could overlap, I was bending the truth a little bit there because actually, when two carbon atoms get together, the nuclei of each of the carbon atoms affects the paths of the electrons on the other carbon atom. And so consequently, the original orbitals sort of get remapped. The electrons don't reside where they normally do. And they end up existing in what we refer to as a hybrid orbital, something that's in between an s orbital and a p orbital. And again, it's because of the interaction of the nuclei with electrons on adjacent atoms. All right, so we need to look a little deeper then into why those hybrid orbitals form. Why would electrons change the boundaries then of their own orbital, and what shapes do these new orbitals take? Okay, the simplest way to start this discussion about hybridized orbitals is to just show you a quick example. For instance, methane, CH4. If we draw its Lewis structure, it's very simple. It's got 8 valence electrons, 4 from the carbon, 1 from each of the hydrogens. It ends up being a 4-legged molecule. And again, if 4 legs, we said last week, would arrange themselves as far away from each other as possible, which would be in the shape of a tetrahedron. Now, this is in the formation of CH4, but if we were to look at carbon, when it's just sitting at home alone, say it doesn't have the hydrogens attached, just a carbon atom. Well, its ground state of electron distribution looks like this. You just went over that 1s2, 2s2 business in lecture. Well, now we know that the outermost shell of carbon, it would have a 1s2, but its outermost shell, which is where all the action happens, its outermost shell would be a 2s2 and a 2p2. Now, that's kind of curious because the carbon, we know that 2s is spherical in shape, and the 2p, where the electrons are, these are dumbbell shaped, but they're at 90 degrees to one another. So there's like a dumbbell along the z-axis, one along the x-axis, and one along the y-axis. Yet, when carbon forms this methane molecule, nothing is 90 degrees apart like the p orbitals. Nothing looks spherical here. This thing takes the shape of a tetrahedron. Something apparently has happened to the original orbitals. They sort of got remapped, so to speak. Well, you can understand how this might happen. I mean, if you think about the solar system sort of like an atom, where the sun is the nucleus and the planets are in orbit around it. Well, we keep nice circular orbits around that center, that gravity sink in the middle of our solar system, because there's nothing else really pulling on the planet other than that big gravity well. But what if we were to bring in another star, closer, another nucleus, close to our solar system? Clearly that would affect the path of the orbits of the planets. Well, when the formation of methane happens and the nuclei of the hydrogens begin to move in on the carbon, it's as if we brought in 4 small suns into our solar system. Well, of course you'd expect that to affect the path of the electrons, the path of the planets. And sure enough, the orbitals actually get remapped into a tetrahedral shape. These are the orbitals that we refer to as the hybrid orbitals, because they no longer look like s orbitals and they no longer look like p orbitals. They look like something in between. I drew one on the board just a second ago. It's that double-lobed orbital, shrunken on one side, big on the other. It appears that when we map out the electrons in methane, the electrons seem to be residing in an orbital of that shape. And all of these hybrid orbitals seem to look exactly the same. This is why when we begin to look at the bonds in methane, we don't see any difference in the bonds. The bond length and the bond strength are all identical. Well, that wouldn't be the case if they retained their original orbital shapes. One bond would definitely be different than the others. So apparently something has happened, sort of mathematically averaged these atomic orbitals into what we refer to as the molecular orbitals. All right, so let's draw a box diagram and kind of explain how this happened. You'll notice, however, that the carbon in this Lewis structure picture really has to provide 1 electron for each of the hydrogens. The hydrogen is bringing the other electron to the shared pair between the two of them. So something must have happened to the carbon in between the time it's just sitting at home alone and the hydrogens begin to close in on it. As a matter of fact, apparently there must be some intermediate excited state where the carbon actually promotes an electron up into this vacant orbital. Because according to our picture, carbon has provided 4 bonding sites for the hydrogens, meaning provided 4 single electrons for the hydrogens to latch onto. Well, in its ground state, that's not the case. So we propose that there's an intermediate excited state where the 2s electrons get split up, and one of them gets promoted into that uppermost vacant orbital, the 2p. All right, so this might explain why the carbon could provide 4 single bonding sites, but again does not explain the fact that one of the bonds doesn't look different than the other 3. They all look identical to one another. And when we map out where the electrons reside, it doesn't look like an S and it doesn't look like a P. It looks like something in between. So this S orbital and these 3 P orbitals essentially get sort of remapped into 4 equivalent orbitals that look like this. They're dumbbell shaped, but shrunken lobes on one side and large on the other. So these 4 atomic orbitals, as the hydrogens close in, get remapped into these 4 equivalent orbitals. Now here's what's interesting. These 4 orbitals are going to arrange themselves around that center nucleus as far away from each other as possible, because that's where the shared electrons are going to live. So that means they're going to take the shape of a tetrahedron, sort of like this, with a lobe down in front. So a little cluster of hybrid orbitals that now have taken the shape of a tetrahedron. Each one has an electron in it. I've spread the electrons out. So now the hydrogens can come in here with their s orbital and form a sigma bond with these hybrid orbitals that are on the carbon. All right, well, this, you can see this is kind of an ugly mess. So in order to simplify things, we'll just use a box diagram to kind of show that these 4 orbitals now, these 4 atomic orbitals, no longer have retained their original shape. They are now 4 equivalent hybrid orbitals. So we call this the hybridized state. I'm going to draw all 4 boxes together. This is just to imply that they're now all of equivalent energy and equivalent shape. And now I've got an electron in each one. This explains how I could have 4 equivalent sigma bonds to those 4 hydrogen atoms. All right, so in essence what I've done is made a box diagram that was consistent with my Lewis structure. And I can't stress this enough. You have to start with a correct Lewis structure first. It shows how your electrons are distributed in such a way that the central atom is providing 1 electron for each bond. Can you make your box diagram fit that picture? Meaning, can we spread the electrons out in such a way that it's consistent with that Lewis structure? In this case, yes. We had exactly 4 electrons. We could spread them out in such a way that there was 1 in each box. Well, then we have to explain, well, why are the bonds all identical, and why, if it stayed like this, then one would look different than the other 3. And it wouldn't take the shape of a tetrahedron, and it'd have these 90-degree angles in it. All right, well, that doesn't happen. Again, as the hydrogens move in, the orbitals get remapped into these 4 equivalent hybrid orbitals. Now, since we used the S box and we used all 3 of the P's, so we had an S and a P and a P and a P, they refer to these hybrid orbitals, we're so clever the way we come up with these names, as the sp3 hybrids. So whenever there's 4 hybrids, it's because we used the S box and all 3 of the P boxes. So this is not like the number of electrons that were in the P orbital. This is just how many orbitals we actually use to make our hybrids. All right, so anytime you have a 4-legged molecule, then that means that it needed 4 hybrid orbitals in order to do the job. So every time we've had a 4-legged molecule, it turns out that it's sp3 hybridized. Okay, one important aspect that we have to introduce here early in the game is that these hybrid orbitals that we're about to look at, or that we're going to look at in a little more detail, really have 2 responsibilities. Since they can't form pi bonds, it turns out that their big responsibility is they form all the sigma bonds that are in a molecule, kind of the skeletal structure of the molecule. But they also provide housing for any lone pairs that are on the central atom. All right, so, and it's pretty easy then to draw a box diagram that's consistent with the picture if we can distribute the electrons in such a way that some of the orbitals contain pairs to represent these lone pairs. All right, as a matter of fact, let me just show you a quick example. Okay, this example has a lone pair in one of the hybrid orbitals. Now, if you recall when we were doing this last week, the Lewis structure of ammonia, by the way, looks like this. It's only got 8 valence electrons. The nitrogen ends up with one leg being a lone pair, the other 3 legs being hydrogens. Now, when we counted the number of legs on this molecule last week, remember we counted the lone pair because it took up a position on the tetrahedral shape that this is. But again, it was kind of invisible. But now we want to look a little closer at that lone pair because it's living inside one of the hybrid orbitals. So this means that essentially nitrogen is going to need 4 hybrid orbitals because the sigma bond here with the hydrogen, it's going to need a hybrid. Here we need a hybrid, and we need a hybrid to house that lone pair. So last week when we were counting the number of legs on a molecule, we were really counting the number of hybrid orbitals that we needed. All right, so in this case, I know I'm going to need 4. Well, let's look at the ground state electron arrangement of the nitrogen. It's a 1s2, 2s2, 2p3. All right, so here's the 2s2, here's the 2p3, and put that in here. But according to my Lewis structure, apparently nitrogen is going to provide 3 single electrons for the hydrogens, but it's going to retain 1 pair that's going to reside in one of those orbitals, a lone pair. Well, apparently I don't have to rearrange my electrons then at all. My box diagram shows a pair here, so that could represent the lone pair that's on the nitrogen. Here's the 3 single ones that could represent potential bonding sites then for the hydrogens to latch onto. So there was really no need then for the nitrogen to promote an electron or move anything around. It just turns out coincidentally that the excited state would have no change. We'll just leave the electrons where they are. But we do know something about ammonia. We know that the map of this this lone pair up here and the sigma bonds don't look like S's, they don't look like P's, they look like the hybrids. So this is always consistent with this whole hybridization paradigm. All right, well, in this case, we need to use all 4 of the boxes again, just like we did for the methane example. But this time, one of our hybrid orbitals is going to contain a pair. So this is consistent with my picture, shows that there's a lone pair in one of the hybrids, and I've got 3 other hybrids available for sigma bonding with those hydrogens. So in essence, here's what I've got. I've got these 4 hybrid orbitals shaped in a tetrahedron with one down here in front. This one's got a pair of electrons up here. Each of these has 1. The hydrogens then can form a sigma bond here with each of these 3 lobes and leave that lone pair residing in one of the hybrids. Now again, we use the S box, all 3 of the P boxes. This is a 4-legged molecule, and 4-legged molecules are sp3 hybridized. Okay, well, to illustrate, I'm gonna roll the clock back a little bit, and let's do a couple examples of molecules that are on the underside of the rule of 8. Last week we talked about expanded octets. I want to show you a couple examples that are called incomplete octets. They have their own little rule of less than 8. All right, well, let me show you those. Okay, well, on the underside of the rule of 8, you find this notable exception. It's BeCl2, beryllium chloride. Turns out it's only got 16 electrons that it's bringing to the dance. 7 from each of the chlorine. The beryllium it's in group 2, so it has 2 valence electrons, so only 16. When you draw the Lewis structure and you pay off everybody on the outside, you find that sure enough you're short for the beryllium. That uses up all 16 electrons to give the chlorines each 8. And you think, well, why not double bond? Just take a lone pair and double bond in here with the beryllium. And yeah, that would obey the rule of 8, but unfortunately beryllium doesn't do that. And so consequently it is an exception to the rule of 8. It has its own little rule of 4. All right, well, we can kind of do a box diagram that shows why this might be the case. I mean, if we look at the the electron arrangement for beryllium, the central atom, it's a 1s2, 2s2. It's only got 4 electrons. Its outermost shell is the one we're interested in, though. That's the 2s2. All right, so here's the 2s with the 2 electrons in it, little arrows to indicate up, one down. There's a vacant 2p out here. Even though it doesn't have any electrons in it, those orbitals are available if I want to stick an electron out there. And it looks as if I may want to, because look at my Lewis structure. The Lewis structure says that apparently when the chlorines closed in on this beryllium, the beryllium provided 2 bonding sites, meaning an electron in each wing. So that means that the beryllium must have split up this pair of electrons that it had in the 2s, at least just prior to bonding. All right, so we propose that there's an excited state here, where sure enough, this electron gets split up and gets promoted into that first available 2p. All right, so this might explain then why the beryllium could provide 2 bonding sites. It could split up its 2 electrons, not inconceivable. Doesn't explain, however, why these 2 bonds look identical, and they don't look like S's or P's. They look like something in between, like 2 hybrid orbitals. And so the beryllium apparently forms a hybrid orbital that sticks out in one direction, and then a hybrid orbital that sticks out in the other direction, each one with an available electron in it. All right, so apparently then it's going to hybridize just 2 of these orbitals. We're going to leave these other 2 vacant p's alone. Remember that they're still full dumbbell shape. All right, so those unhybridized leftover orbitals, as long as they have no electrons in them, they're of no concern to us. We're only concerned with the ones that we need to remap that have electrons in them that are going to share now with the peripheral atoms. All right, so in the hybridized state here, we're only going to use an S box and a P box. So these are referred to as the SP hybrids. Now you can see that each one's got an electron in it, so that's a perfect setup so that each one could form a sigma bond then with the chlorine that's out here. And again, this is consistent with our picture. We see 2 single bonds. We see 2 electrons available in the beryllium to do those 2 single bonds. And sure enough, if we can just imagine that they're going to be hybridized, when we look at the maps of where these electrons actually are, it looks like this. So again, it doesn't look like S's or P's, it looks like hybrids. So it turns out then every time we've had a 2-legged molecule, it's been sp hybridized. All right, well, let's look at one more that's under the rule of 8, because it kind of explains the very next level of hybridization where we're going to use 3 boxes. Okay, here's the other notable exception on the underside of the rule of 8, an incomplete octet. BCl3. Turns out this compound with 24 valence electrons, if you total them up, the chlorines are each bringing 7, the boron brought 3. Okay, so it turns out that if we take those 24 electrons and distribute them the way I usually do, put in the spokes, give everybody on the outside the 3 lone pair they want, we see that the boron is short. It only has 3 pair of electrons around it. And like before, we could make one of the chlorines kick in and double bond, but it turns out boron doesn't do that. All right, so if this is the true Lewis structure then for BCl3, because it doesn't appear to have resonance, there does not appear to be a double bond in it, this means that the boron provided 3 single electrons, 1 in each of 3 hybrid orbitals, to overlap with the chlorines that are there. Well, conveniently, boron brings 3 electrons to the dance. As a matter of fact, its electron arrangement, 1s2, 2s2, 2p1, shows 3 valence electrons. Well, here's its ground state then. It's got a 2s2 arrangement, pair of electrons there. 2p1 got 1 electron there. But apparently there's something that happens as the chlorines close in. An electron gets promoted into a vacant orbital because it provided 3 single ones. All right, so let's put the excited state here. Single electron in the 2s now. We'll take up the next available 2p and spread all the electrons out. All right, so this explains how the boron could provide 3 bonding sites, but again, doesn't explain why they all seem to look like hybrids and not like S's or P's. But again, it's the nuclei of the chlorines that have affected the path that the electrons take, and consequently, their maps have been changed. So we're only going to use the S box and 2 of the P boxes. We're going to leave behind one unhybridized P orbital. Like we did before with the BeCl2, we left 2 of them behind. But this time we're going to use 3 of the boxes for our hybrids. So remember, now we've got 3 hybrid orbitals that look like this. Only they're going to arrange themselves as far away from each other as possible, very likely in the form of a triangle. Well, that's kind of what we anticipate for 3-legged molecules. 3-legged molecules turn out to be sp2 hybridized. And you can see here that the boron then has 1 available electron in each of those sp2 hybrids to provide a bonding site then for the chlorine to attach to out here. So each of these orbitals would have an electron in it. Consistent with the Lewis structure, consistent with the actual measurements of the bonds and the shape of this molecule. So this hybridization model has been around a long time, and all the circumstantial evidence that we have about mapping the electron seems to bear this out. All right, so it turns out, yeah, every time you saw a 3-legged molecule, it was sp2 hybridized. So drawing the correct Lewis structure pretty much leads you then to know how many of the boxes you're going to need to make your hybrid orbitals. Not too difficult then to make a box diagram that's consistent with our picture. All right, so now we've looked at 2-legged ones, that's sp hybridized. We've looked at 3-legged ones, that's sp2, because you'll need the s orbital and 2 p's. Then 4-legged molecule, that was the methane, I did it first. That's sp3 hybridized. Well, at that point, with 4 legs, you've used up all of the p orbitals. So that means when we get to an expanded octet, the 5-legged and 6-legged molecules that we saw last week, now we're going to need some more orbitals. We've run out. We've used the s, we've used all 3 of the p's. That means we're going to have to dip into the d orbitals. This is exactly why you can't have an expanded octet until you get to the 3rd level in the periodic table, because that's where suddenly the 3rd shell has a d sublevel that's available for us to form bonds with. All right, well, let's look quickly at an expanded octet. Okay, well, here's where things get kind of interesting. When we get to the expanded octets, like I said, you have to be in the 3rd period or lower because we need some d orbitals to use in order to make more than 4 legs. And so consequently, if we do an example that we did last week, PCl5. Now, when we do PCl5, remember it takes the shape of a trigonal bipyramid. It's got 5 legs, and all of the legs are occupied. Okay, so the molecular shape's a trigonal bipyramid. And it appears from the Lewis structure that the phosphorus had to provide 5 bonding sites for the 5 chlorines. So that means at some point the phosphorus had to spread its electrons out to put all 5 of them, 1 in each orbital. All right, so we kind of know what's going to happen. Once you look at the Lewis structure, you see where this is going to head. And just not by coincidence, but pretty much by design, look at the outermost shell of phosphorus. If you write out its electron arrangement, it's a 1s2, 2s2, 2p6, 3s2, 3p3. It's got 5 valence electrons. Perfect. It can spread all 5 out and provide a bonding site for each of the 5 chlorines. All right, so here's its ground state. 3s2, 3p3. That's what I've got here for its outermost shell. It's pretty clear that if we want to promote that electron into a vacant orbital, the next vacant orbital is up here in the 3d. This is why we couldn't do this with atoms that were in the 2nd shell. There is no 2d subshell. They have to obey the rule of 8. But you get to the 3rd period, no, now it's wide open. All right, so if we promote that electron then up into that first vacant orbital, we get an intermediate excited state that has 1 electron now in the 3s, 1 in each of the 3p orbitals, and 1 in the 3d orbital. So this explains how phosphorus could provide 5 bonding sites. But again, it doesn't go near explaining the shapes of these orbitals. They all look like hybrids. They don't look like S's anymore, or P's, or D's. They all look identical to one another. That same big lobe on one side, little lobe on the other. And all 5 of them take a flat triangle shape here, and then there are 2 axial positions like this. Takes the shape of a trigonal bipyramid. All right, in order to minimize repulsion effects. All right, so every 5-legged molecule pretty much ended up doing this. It used its S box, all 3 of the p boxes and 1 of the d boxes to make 5 equivalent hybrid orbitals. 5 equivalent hybrid orbitals, each with a single electron in it, to represent the 5 sigma bonds that the phosphorus had to form with the 5 chlorines. And guess what we cleverly call these now that we use the S box, all 3 of the p boxes, and a d box? They're called the sp3d hybrids. Again, it's just it just signifies how many of the boxes we actually used in order to make our hybrid orbitals. And if you draw the correct Lewis structure for the molecule, it's very easy to draw a consistent box diagram that matches your picture. All right, well, let me do a couple more of these, and then we'll move to the report sheet and take a look at it. Okay, here's another expanded octet that we looked at last week, was SF6, sulfur hexafluoride. Ended up being an octahedron, had 6 legs, all the legs occupied, so the molecular shape and the electron pair arrangement were both octahedral. All right, so it appears from the Lewis structure that the sulfur has to provide 6 single electrons for the 6 fluorines to attach to here. And again, not by coincidence, but pretty much by design, sulfur, if we write out its electron arrangement, ends with a 3s2, 3p4. It's got 6 valence electrons. That's perfect. All right, so its ground state kind of looks like this. 2 electrons in the 3s, 4 electrons in the 3p. Remember, they always go in one at a time first, and then they go back and pair up. So this is what it would look like. 3s2, 3p4, and there's a 3d out here with no electrons in it at all. Well, apparently I'm going to need some of these because I need as many hybrid orbitals as I have legs, and I got 6 legs. So I'm going to need the S box, all 3 of the P boxes, and a couple of the D boxes this time. Well, conveniently, if I were to spread the electrons out, and according to the Lewis structure, sulfur does exactly that. It spreads all 6 out. I'm going to have to split up both of these pairs in that intermediate excited state just prior to bonding. So that means that one of these electrons is going to move up into one of the vacant d orbitals, and one of these will move up. We end up with a 3s with a single electron in it, a 3p with 3 singles, and a 3d with a single in the first 2. All right, well, this seems logical that we'd have 6 single electrons, but again, they get remapped because of the fluorine's influence, and they end up looking exactly the same. So to illustrate that, we'll draw them as a matched set of 6. Drawing them as a matched set, again, just kind of signifies they're all identical and all of the same energy now. So I'm going to take those 6 boxes and I'm going to make my hybrids. There's a single electron in each one. So that's perfect for a sigma bond, sigma bond, sigma, 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 sigma with the fluorines. And again, since we use the S box, all 3 of the P's and 2 of the D's, they call these the sp3d2 hybrids. Now this means that anytime you saw a 6-legged molecule, it had to have used these 6 boxes. This is the hybridization type then for all 6-legged molecules, regardless if one of those legs was a lone pair. As a matter of fact, I'll do one here in a second. I mean, if one of them was a lone pair, chances are I'd have a pair in one of these boxes here to represent that. There would have been some extra electrons to represent those lone pairs. Okay, so 6 legs, regardless of whether they're lone pairs or bonded atoms, require 6 boxes. That means sp3d2. 5 legs, sp3d. All right, so now we've looked at them all. 2-legged ones, sp hybridized. 3-legged ones, sp2. 4-legged ones, sp3. You get to 5-legged ones, it's sp3d, and you get to 6, it's sp3d2. All right, on your report sheet, I've summarized this in kind of a table, so when we get to the report sheet, we'll take a quick look at it. But let me do another example of this, only let's put some lone pairs in some of these boxes, and you'll see how easy it is to make a box diagram that's consistent with your Lewis structure. Okay, here's another expanded octet that was actually in our lab last week on molecular models. It was IBR5. It ended up being an octahedron, but one of the legs turned out to be a lone pair, which gave it a square pyramidal shape, square pyramid. So that one lone pair sort of being invisible. All right, so now, just looking carefully at our Lewis structure, we can kind of see where this game is going. We know that the iodine has to provide 5 single electrons, 1 for each of the bromines that are there that's going to latch on to it, So 5 hybrid orbitals, each with a single, but the 6th hybrid orbital is going to have a pair in it. All right, we know this is a 6-legged molecule, and the hybrid orbitals, it's their responsibility to house that lone pair. All right, so let's see if we've got the right number of electrons in iodine to be consistent with that picture. Here's its electron arrangement. It's a krypton core with a 5s2, 4d10, 5p5. So here's its outermost shell, 5s2, 5p5. All right, well, ground state then, 2 electrons in the 5s, 5 electrons in the 5p, and notice how I put them in. I put them in singly first, and then I went back and paired them up with the down arrow. And there's only 5, and there's a vacant 5d sublevel that we may end up using, because again, this thing has 6 legs. I already know what its hybridization type is. It's sp3d2. I need all 6 of those orbitals to make these 6 hybrids. All right, well, that means I'm going to go out to these first 2 boxes in the 5d. Could I arrange those electrons in such a way that there would be 5 single electrons in one pair? Well, yeah, exactly. I have 7 electrons. This is perfect. If I were to just split up 2 of these pairs, look what's happening. There'd end up being 5 singles then, and 1 pair to represent my lone pair that's on my Lewis structure. So yeah, I can make a box diagram consistent with that. In the excited state, apparently, though, those electrons do get promoted, leaving 3 single electrons then in the 5p, and a couple single electrons out here in the 5d. So we're going to hybridize. We're going to use the S box, all 3 of the p's, 2 of the d's to make our hybridized state. Sure enough, we end up with a matched set of 6. A lone pair in the first box, and it wouldn't matter which box I put it in. Remember, they're all identical to one another now. And 5 single electrons. There were just enough electrons in the valence shell of iodine to do exactly what the Lewis structure said it was going to do. It was going to do 5 sigma bonds and a lone pair. So these were my sp3d2 hybrids that are responsible then for creating this molecule, the IBR5. All right, this is so much fun. Let's just do one more. Okay, well, here is another one that was on last week's lab, was xenon difluoride, XEF2. If you recall, it was a linear molecule based on a trigonal bipyramid. It had 5 legs, 3 of them being lone pairs and 2 of them being bonded atoms. And since the lone pairs have to go on the triangle, it ended up being a straight line with the xenon. All right, well, can we do a box diagram consistent with that? Well, a quick examination shows the xenon apparently provides, for these 5 legs, 2 of them are single electrons, but the other 3 legs have to have pairs in them. So we're going to need 5 hybrid orbitals, but we need to spread the electrons out in such a way that there's 2 singles and 3 pair. All right, well, that's fortunate because xenon has 8 electrons in its outermost shell. Its electron arrangement is a krypton core, 5s2, 4d10, 5p6. So 8 electrons. Let's start at ground state. 5s2, 5p6. Everybody's packed. 5d is vacant. Now, could I split up enough of those electrons so that I would end up with 3 pair and 2 singles? Well, sure. What if I just split up 1 pair? That'd leave me those 3 pair. I'll promote 1 electron up here. That's going to give me 3 lone pair and 2 singles, exactly what my Lewis structure says are there. So let's draw an excited state then, where we've still got the 5s2, because we didn't have to split it up. We still got a couple pair in the 5p. We've got a single in that last 5p, and we put a single out here in that first 5d. Now, we already knew we were only going to use 1 of the D boxes, right? Because this is a 5-legged molecule, so that's sp3d hybridized. So we knew where we were headed with this. All right, well, sure enough, this is consistent with the picture. 3 lone pair, 2 singles, but we have to draw the hybridized state just to imply that, yeah, these 5 orbitals are now equivalent to one another. And sure enough, there's a pair in 3 of them, and singles in the other 2 to represent sigma bond, lone pair, lone pair, lone pair. These are the sp3d hybrids then that make up this molecule, xenon difluoride. Okay, so for today's lab, we're going to go to the report sheet here in a second. I'm going to build the molecular models for you again. The first thing it's going to ask you for is how many sigma bonds are on that central atom and how many lone pairs, and so that total will give you the total number of legs the molecule has. So I'll walk you through the report sheet. Again, it pretty much goes hand in hand with what we discussed last week, only we're adding this little twist of drawing box diagrams for everything. All right, well, we need to come back though and talk a little bit once we get to the report sheet about electronegativity. So you'll see when we get to the bottom of the report sheet. All right, well, let's go there. Okay, first of all, I can't stress this enough that you should read through all of the lab text. I wrote a very elaborate set of instructions for this that goes through each type of hybridization and the corresponding box diagram. We're going to have you do 6 molecules for this exercise, and as you draw the Lewis structures of each of these 6, if you leaf back through the lab text, you'll find an example that's very similar, at least with the same number of legs, same number of lone pairs as the Lewis structure that you're trying to do. So again, just keep referring back to the lab text, and I'm sure that you'll find that you can walk your way through all of these different box diagrams. Now at the end of the instructions, there's a summary, this table, which is on page 8, which says the number of legs over here in the left-hand column where they say the number of required hybrid orbitals. Same thing, because remember that the hybrid orbitals take care of the lone pairs and the peripheral atoms, so that basically is all of the legs. A two-legged molecule, which we established last week in lab is linear, would be sp hybridized because you'd only need 2 hybrids to do the 2 legs. Three-legged molecule, sp2. So again, all the way down the line, we already know, once we've drawn the Lewis structure and count how many legs it has, we know what the hybridization scheme is going to be. So it really kind of gives away then which example you'd want to go back and look at in order to figure out how to draw the corresponding box diagram. All right, well, let's do the first one. I just wanted to kind of walk you through this. The first column that they've got here is CF4. It turns out the Lewis structure, and you'll see when you draw the Lewis structure, just go back and look at our rules from last week on how you do these. You count up all of the valence electrons, again, put the central atom in the middle, peripheral atoms around it, put in the spokes, pay off everybody on the outside as long as you've got enough electrons. You end up with CF4 looking like this, a nice tetrahedron. All right, now with that in mind, they want to know how many sigma bonds this molecule has. Well, from our discussion, you know that every peripheral atom gets a sigma bond. All right, so if that's the case, then with 4 bonded atoms, pretty clear that how many sigma bonds there are there. They want to know how many lone pairs are on the central atom. Well, in this case, you're going to find none. And the sum of these 2 then would be the number of legs that the molecule has. Total, because remember, we counted the number of bonded atoms, which each would get a sigma bond, and the number of lone pairs that are on the central atom. With the total number of legs, you can go to the table we were just discussing that's on page 8 and see, well, what type of hybridization goes along with that many legs. Remember, if you need 2 legs, this would be sp. If you need 3 legs total, sp2, 4 legs is sp3, 5 sp3d, and 6 legs is sp3d2. Well then, we're going to go on and ask for the box diagrams and the electron distributions. Well, I've done some examples for you here on the video, and if you go back through the lab text, I think you can find a 4-legged molecule with carbon or one of its family members as the central atom, and this will walk you through the box diagrams that you need for its ground state. Let me scooch this up. Its excited state, and its hybridized state. Now they also want to know then, well, what's the electron pair arrangement? This is something from last week's lab. We want to know which of the 5 fundamental electron pair arrangements did it take. Remember, 2 legs is linear, 3 is trigonal planar, 4 is tetrahedral, 5 trigonal bipyramid, and 6 is octahedral. Then we want to know, well, what's the molecular shape? If you recall, that means just look at the electron pair arrangement and sort of treat the lone pairs as if they're invisible and describe just the remaining atoms and what their spatial arrangement is. All right, and then we want the bond angle, again from last week's lab. That's the angle between the peripheral atoms. Now here's something new. Are the individual bonds polar? And is the molecule polar? At this point, I want to cut away to the blackboard because this takes a little bit of an explanation about the difference between these two questions. All right, well, let's cut away. All right, well, in the discussion of the polarity of individual bonds, it turns out that when two nonmetals share electrons with each other, they rarely do it equally. Generally, the pull of one of the atoms is a little greater than the other, and the electrons will spend more time circling one atom's nucleus than the other. Well, this attraction that an atom has for shared electrons is something called electronegativity. This was a term developed by Linus Pauling, won a Nobel Prize for this. He used the concept of ionization energy and electron affinity and came up with kind of an easy to read scale of electronegativity, which just is a measure, literally, of the attraction that an atom has for shared electrons. Now it turns out that this scale is pretty easy. The electronegativity scale on the periodic table, it goes from 0 to 4. 4 is the top dog. So on the periodic table, electronegativity increases going up in this corner. Turns out fluorine is the top dog. It's got a value of 4. And there's a table of this in your text on page 407. They've got a table of all the electronegativities of all the elements. And actually down here, cesium, I don't think actually goes to 0. It's got an electronegativity of about 0.6. All right, so it turns out that when two atoms bond to each other, like I said, it's rarely an equal sharing. All right, let me erase this and I'll show you something. Okay, well, like I just said, when two nonmetals share electrons, they rarely do it equally. The only time I can think of where it's a perfect equal sharing of electrons is if the two atoms are identical to one another. For instance, the diatomic elements. Those would be considered completely non-polar bonds. When they use the word polar, they don't mean cold. They just mean lopsided, like two poles, north and south. So if two atoms share electrons perfectly equally with one another, they refer to that as a non-polar bond. But if there's an unequal sharing, that's referred to as a polar bond. Well, it turns out more often than not, you end up with polarity in a bond because, like I said, unless the two atoms are identical to one another, there's going to be a difference in their electronegativity. And the shared electron pair spends more time orbiting the more electronegative of the two that are sharing the electrons. So for instance, if in a molecule we had a carbon and an oxygen together sharing electrons between the two, well, it turns out that if we look up carbon on the periodic table and oxygen on the periodic table, as a matter of fact, let me find their numbers. Carbon's got an electronegativity of 2.5. The oxygen's got one of 3.5. So oxygen being closer to the upper right-hand corner of the periodic table, sure enough, the electrons spend more time down here at this end of the bond, literally orbiting the oxygen more often than they orbit the carbon. Well, this causes a certain lopsidedness then, a polarity in the bond, where this end of the bond becomes slightly negative and this end of the bond becomes slightly positive. As a matter of fact, let me put a little small Greek delta. Now remember, we used a delta symbol, you know, the triangle, to mean the change in something. Well, I consider the small Greek delta just to be a small change in something. So that little delta with a negative sign just means a slight negative charge at that end and a slight positive charge at this end of the bond. All right, well, it turns out that in order for this to be noticeable, this unequal sharing, this is where Linus Pauling's electronegativity scale really comes into play. He said, you know, when two atoms are identical to one another and their electronegativities are the same, they share the electrons perfectly equally. That's called a nonpolar bond. And when they're different from one another and it's unequal, we'll call that a polar bond. But it turns out if they differ in electronegativity by just a little bit, it's hardly noticeable. It seems very nonpolar. As a matter of fact, their electronegativity values have to differ by more than 0.5, 0.5 or greater for it to be a noticeable lopsidedness in the bond. All right, well, let me erase this and we'll put the rules here about, well, when do you consider a sharing of electrons to be equal, or when do you consider them to be unequal? Okay, electronegativity, scale, and polarity. If I'm going to use the symbol delta En to mean the difference in the electronegativity between two elements that are sharing electrons. If that delta En equals 0, then you've got a completely nonpolar bond, meaning that there's no extra pull on the electrons from either side. For instance, two chlorines linked to one another. They both have an electronegativity value of 3. Obviously, they're the same atom. So they're both pulling exactly the same on those shared electrons. That's a completely nonpolar bond. However, it turns out that in order to be considered polar, the difference in the electronegativity has to at least be 0.5 or greater. If, like iodine and bromine, I think when they're together, they only differ by about 0.3. So when they share electrons between an iodine and a bromine, it turns out to be a nonpolar bond between the two of them. But here's an example of a polar bond. Here's carbon and chlorine. Now, again, the carbon has a value. I went and looked it up on in the table in your textbook on page 407, or you can just type in electronegativity in a Google search. You'll get like a million tables that come up with the electronegativity values. But carbon's got a value of 2.5, chlorine's got a value of 3. Well, that's on the edge, but sure enough, that's considered a polar bond. The electrons spend way more time down here around the chlorine than they do around the carbon, making this end of the bond slightly negative, this end of the bond slightly positive. All right, so when the book or the lab packet asks you, are the bonds in this molecule polar or not? You're going to have to go to that table of electronegativity values, unless you can hold them all in your head, and just look at the two atoms that they're talking about and say, well, let's look up their electronegativity values. Easy enough to see the difference. And if the difference is at least 0.5, then you can consider that bond to be a polar bond. Now they go on to ask you one more question. They say, well, is the whole molecule polar? Is it lopsided? All right, well now, as opposed to looking at an individual bond, we're going to zoom back and look at the whole molecule. Now this really has nothing to do with electronegativity at this point. This has to do with the symmetry of the molecule. All right, well let me get rid of this and I'll show you. All right, the polarity of an entire molecule is a completely different question than the polarity of individual bonds. It turns out that this has only to do with the symmetry of the molecule. Again, it's lopsidedness as a whole. So we're going to zoom back from the individual bonds, like I said earlier, and just look at the entire molecule. Now it turns out if it's asymmetric, meaning if it has any weird lopsidedness to it, or electronic lopsidedness to it, they consider that molecule to be polar, meaning that one side of the molecule is more negative than the other, giving it two poles. This ultimately makes it act kind of like a little magnet. Polar molecules have unique properties to them because they stick together real well. You can understand why, because they, like I said, act like little magnets, little North Pole, South Pole. But molecules that are very symmetric, nonpolar molecules, where all the legs on the structure are identical to one another, or if there's any odd legs, they're equally balanced on opposite sides of the molecule, sort of like a vector sum. If all the vectors point out in equal magnitudes, equal and opposite directions, then they cancel each other out. So a nonpolar molecule would have like a 0 vector sum. All right, so just meaning that you have to really build a tinker toy to look at that. I mean, for instance, here's the one we had for CO2. Double bond on both sides. Now, granted, the first question about are the bonds polar, well, then you just look at one side and you'd say, well, between carbon and oxygen, is that unequal or equal? Well, we had to look up their electronegativities. But then they ask you, is the whole molecule polar? Well, now you just zoom back and look at the whole molecule, and you don't even have to ask about electronegativity. You want to know, is the molecule symmetric or not? Well, in this case, yeah, it is. There's a polar bond, but it's pointing out in this direction. There's an equal and opposite one in that direction. This is a perfectly symmetric molecule. Consequently, it's nonpolar. So you can see that the two are not mutually inclusive. A molecule can have polar bonds in it, yet if it's symmetric, the whole molecule itself is considered to be nonpolar. All right, now a three-legged molecule, this is a two-legged one. A three-legged molecule can be polar when one of the legs is different than the other two. For instance, if all of these were red and they were all equal to each other, then that would be nonpolar. But in this situation where you've got two different atoms on two of the legs of the triangle and then one here, this is going to have some lopsidedness to it, and consequently this would be a polar molecule. Again, there's no issue about whether the bonds are polar or not. It's the symmetry of the molecule that dictates whether the whole molecule is polar or not. Okay, well, there's a three-legged one. We did some four-legged ones. Let me see if I can find that. Oh, it's sitting right, yeah, here we go. Now, can you understand if you had a four-legged molecule and all the legs were occupied? This is perfectly symmetric. I mean, there's no lopsidedness to it. There's no north side, south side kind of to the molecule. So, again, this is nonpolar. But what if one of them was a lone pair? Well, now that is some lopsidedness. This side of the molecule definitely looks different than this side of the molecule. This one's going to be much more negative with all that lone pair of electrons sticking up like that. So this is going to be a really lopsided molecule. What if I put two lone pair on there? There were a couple molecules we drew before that had two bonded atoms and two lone pair. Like water. Water looks like this. Well, sure enough, water is very polar. It's got lone pairs sticking out of the top, very negative up here, very positive where the hydrogens are for a water molecule. Okay, so you can understand that building the Tinker Toy model really helps in looking at the symmetry. All right, so let me look at a five-legged one, just quickly here. Now, five-legged, if all of the legs were occupied, then you understand that this would still be a trigonal bipyramid, right? All right, but, and it's perfectly symmetric, so it's nonpolar. Everything on the triangle is equal, all the atoms are the same. This would be perfectly symmetric. But the minute we put a lone pair on, it has to go on the triangle. Notice that introduces some asymmetry to the molecule. This is now a polar molecule. If there were two lone pair, likewise, still polar. Because look, on the triangle it's lopsided. Two of the legs are lone pairs and one's not. So suddenly that's some asymmetry. It wouldn't be symmetric until we finally get to three lone pair. Now that's a symmetric molecule and it's non-polar. So I think you can see that having the model right in front of you really makes a difference. All right, let me pause for a second. I got to recharge my phone and I'll come back and do the six-legged one. Okay, well, here's the six-legged one. Sorry, I had to go run and get my phone charger. Here's the six-legged one, octahedron. If all of the positions of the octahedron are occupied and they're all the same atom, so there's no lopsidedness to it, this is a nonpolar molecule. Again, regardless of whether the bonds are polar. If, however, there's one lone pair, if there's one lone pair, now suddenly there's some asymmetry to this molecule. This side looks different than that side. And sure enough, this is a polar arrangement. I think that we had one like this. It was IBR5 was on last week's. And it looked like a square pyramid based on an octahedron. But today we've got one that's square planar. It's got two lone pair based on an octahedron. So it ends up being square planar. But notice that the lone pairs cancel each other out. All right, so somebody asked me one time, well, is it always going to be polar if there's a lone pair on the central atom? The answer is no, because you can see in this position where the lone pairs are going to go opposite each other, they'll cancel each other out, and this is a nonpolar arrangement of atoms. All right, so now that we've looked at the idea of symmetry of the molecule, and then also looking at the polarity of the individual bonds, that's where you just go to the electronegativity table and look at their values. All right, well, let's go back to the report sheet, and we'll wrap this up. All right, well, now that we've discussed this individual bond polarity, again, what you're going to have to do, since this is carbon and fluorine, you're going to have to look up the electronegativities of those two elements and find out if they're different enough to be considered a polar bond. And again, you can go to page 407 in your textbook to find that table. In terms of the molecule being polar, that has to do with symmetry. And again, we just discussed this. So I'll leave it up to you to decide whether this is a symmetric molecule or not. All right, now PF3, our second one here on page 1. Here's what the molecule is going to end up looking like. It's a tetrahedral electron pair arrangement. It's got one lone pair on it. I'll leave it up to you again to draw the correct Lewis structure. Don't forget to put the lone pairs on your peripheral atoms. And follow the rules. Total up your valence electrons. Central atom is underlined. There, the phosphorus, with the fluorines all around it. Pay everybody off. Again, it ends up with a lone pair on the central atom. You can figure out then how many sigma bonds and how many lone pairs. Remember that that's just the number of peripheral atoms. Lone pairs on the central atom tells you the total number of legs. That tells you the hybridization type. From there, you can find an example. There is one back in the lab text that shows one just like that with 3 bonded atoms and 1 lone pair. And you can pretty much follow the scheme to get the electron distribution and how it's distributed in order to coincide with your Lewis structure. They want the electron pair arrangement, they want the molecular shape, bond angle. Again, you're going to have to look up the electronegativities of phosphorus versus fluorine to determine whether or not that bond is polar. And look at the Tinker Toy model, the molecular model, to decide whether you think that's symmetric or asymmetric enough to be considered polar. All right, here's the last one on page 1, is CLF3. Now this one's a 5-legged molecule, looks like that. You'll find when you do the Lewis structure, if you do it correctly, you should end up with a couple lone pairs on that central element. All right, again, total up the valence electrons, draw a Lewis structure, see if it comes up looking like something like that. All right, well, again, now they want the number of sigma bonds. That's the number of peripheral atoms, so that's easy, there's 3, and the number of lone pairs on the central atom. That tells you how many total legs. That'll lead you to the hybridization type. Then, I'm sure that I put an example back in the text that is a 5-legged molecule with 2 lone pair. So go back and look for it, and you'll find, sure enough, there's a scheme that shows you the box diagrams. They want the electron pair arrangement, the molecular shape, bond angles, and again, the last 2 questions are the individual bonds polar? Well, you have to look up the difference between chlorine and fluorine now and see if that difference exceeds the 0.5 limit. If it's a difference of 0.5 or greater, it's considered to be polar. If it's less than 0.5, it's considered nonpolar. All right, is the molecule polar? Now, the whole molecule, again, symmetry is the answer. I'll leave it up to you to decide. Do you think that's a symmetric molecule or not? All right, well, let me pause here because I got to make some new models, and I'll flip the page over and we'll do the back side. And by the way, I'm really sorry I didn't have any purple ones for fluorine on this. I used green. I'm limited as to the number of models that I have here. So anyway, let me flip the page and we'll look at the last 3. Okay, here we go. Xenon tetrafluoride. Now, this one, as a matter of fact, let me grab a different model. This one I mentioned earlier on when we were talking about symmetry of molecules. This one turns out to be a square planar arrangement. So if you do this correctly with the right number of electrons, you'll find that sure enough you'll end up with 2 lone pair on the xenon. All right, so based on that, should be easy enough for you to figure out how many peripheral atoms there are, how many lone pairs on the central atom, and what type of hybridization requires that many legs. Well, again, there's an example of this back, I think I did one actually earlier. And so you can find a way to write out the ground state distribution of the xenon, its excited state, how the electrons are distributed just prior to bonding, and then the hybridized state where it shows a matched set of 6. Because remember, this is a 6-legged molecule. All right, well, the electron pair arrangement is one of those 5. It's got to be either linear through octahedral, and then the molecular shape is based on looking at the lone pairs as if they're invisible. Bond angles, again, from last week's lab. Are the individual bonds polar? Well, you're going to have to look up xenon and fluorine. I don't know if xenon is listed in our books table. So I'll tell you right now that xenon's electronegativity is 2.6. So you can look up fluorine and then just look at the difference and decide if you think that those individual bonds are polar. Then look at the symmetry of the molecule to determine whether you think that this molecule itself is asymmetric or symmetric. All right, well, let's look at the next one. This is IBR5. Looks very similar to the xenon one we just did, except that it's 6 legs with just 1 lone pair. And I think when you draw the Lewis structure, you'll see that this model is consistent with your Lewis structure. All right, again, not too hard to figure out, well, how many peripheral atoms it has and how many lone pairs on the central atom. That'll tell us the total number of legs. That'll tell us then the hybridization type from that table on page 8. I think I pretty much did an example of this also somewhere in there, but either that or it's in the video earlier. So again, just look up, the ground state electron distribution and then the excited state just prior to bonding. That's where electrons get promoted if necessary. And you just distribute the electrons so that it matches your Lewis structure. If there's lone pairs on your Lewis structure, make sure there's lone pairs left over in your excited state. Well, then we'll just lump all the orbitals together into a matched set to do our hybridized state, just like the examples that I did in the lab text. It wants the electron pair arrangement, molecular shape, bond angle. Individual bonds polar, you're going to have to look up iodine and bromine in that table on 407, page 407 in your text. And again, is the molecule symmetric or asymmetric? I'll leave that up to you as to whether, now remember, if it's asymmetric, it's considered polar. If it's perfectly symmetric, it's considered nonpolar. All right, now this very last one, this COCl2, I did an example of this at the very last in the lab text, and its Lewis structure ends up looking like this. The double bond goes to the oxygen, and then the chlorines are single bonded down here. And I think you'll see that when you put lone pairs on everybody the way you're supposed to, you'll use exactly the right amount of electrons to come up with a Lewis structure consistent with that picture. Now this is the first one where a double bond occurred. And so I got to pause here because I got to show you a couple of pictures that explains, well, how are double bonds being formed when they're only taken care of by the unhybridized p orbitals? All right, well, let me show you. Okay, here's the deal with double bonds. Now it turns out if we look at this molecule, this H2CO that we gave you, it's got a double bond to the oxygen and a single bond to each of these hydrogens. So these are sigma type bonds between the carbon and the hydrogen, sigma here. Remember, the first bond to form between two atoms is always sigma. But here between the carbon and the oxygen, there was a double bond. Only one of those is a sigma and the other one's a pi. Well, that essentially means then that the carbon only needs 3 hybrid orbitals, because the hybrid orbitals don't take care of the pi bonds. Pi bonds are taken care of by unhybridized p orbitals. So the skeletal structure of the molecule is really just the sigma bonds. The pi bonds are sort of an afterthought, sort of superimposed on top of the sigma bond that's there. All right, so if that's the case, then the carbon really only needs 3 hybrids. It's sort of 3-legged. Remember, we counted a double bond as just one leg. So that means it's going to be sp2 hybridized. It's going to take the shape of a triangle. Well, if we look at the oxygen, it's got a sigma bond and 2 lone pairs on it. We could also look at it as the oxygen is being hybridized and also needs 3 hybrids. It would also be sp2 hybridized. So if I just left the pi bond off for a second, let me scooch this up so we can look at it. Here's the carbon with its 3 hybrid orbitals sticking out here. It's 3 sp2 hybrids, 1 to the oxygen, 1 to each of the hydrogens. Here's the oxygen with its 3 hybrid orbitals, its sp2 hybrids, 1 pointed toward the carbon, and one for each of these lone pairs that are back here. All right, so here it is drawn a little bit more elaborately with the lobes. So back here I've got a pair of electrons. Back here I've got a pair of electrons representing these 2 lone pair. Here I've got just a single electron that I'm going to share with the one on the carbon to form a sigma bond. And the carbon's got an electron back here in the back so that the hydrogens can latch on with their electron and make a nice sigma bond back here in the back. But here's what's interesting about the box diagrams, is that in order for carbon to do that, it still needed to spread out its electrons from its ground state. And so in the excited state, an electron does get promoted. But we only need the s and the first 2 p's to make these 3 hybrid orbitals that we needed for this skeletal structure of the molecule. So we called them the sp2 hybrids because we're only using the s box 2 of the p's. So here's the sigma bonds to the 2 hydrogens, and here's the sigma bond to the oxygen. But look at what happened. In this case, the unhybridized leftover p orbitals, which for all of our other examples were vacant, didn't have any electrons left over in these unhybridized leftovers, this time we've got an electron there. Now what's interesting is, when we look at oxygen, the same thing happens. In its hybridized scheme here, where it only needs 3 hybrids, if we only use the S box and the 2 P boxes for oxygen, and notice oxygen's ground state is an S2, and a P4. So that leaves two pair in those first two hybrids and a single. Well, that's exactly what our picture shows. A single for the carbon, for the bond of the carbon, and then two back here to represent the two lone pair that are on the oxygen. All right, well, those are my sp2 hybrids, and sure enough, there's my two lone pair. Here's my sigma bond to the carbon. But that left another electron left over in an unhybridized p orbital. Now, to do this, I'm going to draw the p orbital. The unhybridized p orbital that was left over is right there, going straight through that triangle of sp2 hybrids. There's one on the carbon also, like that. Each one of them had an electron. Let me scooch up here. Each one of them had an electron left over. So that means that they can overlap side to side and form a pi bond. So orbital-wise, this is essentially what this molecule looks like. The molecule C double bond O, H, H2CO. In an orbital sense, then, the sigma bond that's formed between the carbon and oxygen goes right down the middle. It's formed by the hybrid orbitals that the carbon has. And the sigma bonds with the hydrogens, likewise, are the other two hybrids that the carbon has. But it had one leftover p orbital that was still unhybridized in its original dumbbell shape. And it wasn't vacant. It had an electron. Oops, let me scooch that back. It had an electron in it. All right, well, turned out the oxygen likewise had a leftover, unhybridized, full dumbbell p orbital left over, also with an electron in it. How convenient. And so now when they overlap side to side, that accounts for that second additional bond that was formed there. All right, so in that case, you can see that double bonding and triple bonding has to involve electrons that were left over out here in these unhybridized orbitals, and sure enough, that's the case. All right, well, we only gave you one of them to look at. As a matter of fact, let me pull up the sheet here. I think it was at the bottom of page 7. Let me double check here. I think I went through this exact example. Oh, come on, I know you're there. Yeah, right here. At the bottom of page 7, I went through the example for a pi bonding using unhybridized p orbitals. And I did a very similar molecule with carbon and oxygen. And I showed both of their electron arrangement schemes, their box diagrams. Notice again, in each case I left an unhybridized p orbital with an electron in it. And I said here, that's the pi bond formed with the oxygen. This is the pi bond formed with the carbon. At the top of the very next page, I had kind of a poor drawing of it. Let me flip this over and turn and see if it's here. Yeah, there we go. It's this molecule. Instead of chlorines back here, I just simply used hydrogens. But the same kind of picture. I was trying to show the sigma bond going down the center here and the pi bond above and below. So again, I've got something for you right there at the bottom of page 7 that you can at least address when you're doing the report sheet. All right, as a matter of fact, let me go back to that report sheet. That very last one, COCl2, as I mentioned, here's the molecular model. They want to know, well, how many of those are sigma bonds? Remember, when you get a double bond, only one sigma, the other's pi. Then they want to know the number of lone pairs on the central atom. Again, you saw the molecular model, and you've got the Lewis structure there. They want what type of hybridization it is. And again, I directed you to the bottom of page 7 to get this ground state, excited state, and hybridized state distribution. The electron pair arrangement is a two-legged linear, three-legged trigonal planar, that sort of thing. What's the molecular shape, bond angle? And again, now in this case, I should have put room for 2 answers here. Because I want to know, is the carbon oxygen bond polar and is the carbon chlorine bond polar? Because there's actually 2 different bonds there. I should have left space for 2 different answers. So you'll have to look up the electronegativities again of the 2 elements, determine whether or not they differ by 0.5 or greater. Is the molecule polar? Again, that deals with symmetry. I'll leave it up to you to decide whether you think that's symmetric or not. Again, symmetric is nonpolar, asymmetric would be polar. All right, well, I think we can head back to the blackboard now that we've gone over the entire report sheet. And again, the pre-lab has questions on it, very similar. You got to draw a Lewis structure. You've got to answer very similar questions, draw a quick little box diagram. But I think you'll find an example very similar in the lab text that goes along with the pre-lab. Okay, so now again, be sure that you've completed the report sheet. Before you snap a picture of it, please put your name on it. And complete the pre-lab and the quiz that I sent you on molecular structures from last week. Okay, well, let's get back to the blackboard then. Okay, well, that wraps up the exercise on hybridization. Be sure to complete the Lewis structure quiz that I sent you, and the pre-lab for today's lab, and the report sheet, both sides, please. And if you wouldn't mind, put your names on all the papers before you take photos of them, because I get them all mixed up in my printer if I don't have names on them, so that would help. Now, next week, we're going to do one last little demonstration, a chromatography demonstration, and I'm going to attach to it a quiz over today's hybridization lab. So again, I'll ask for one last submission from you next week, and that'll pretty much wrap it up. All right, well, so long until next week. Lab's in the barn. See you then.